So mostly you're going to be seeing stuff in the sky, not my face, but I'll try to have my light on for a minute here. And yeah, and thanks to Preet and Dr. Grosvenor and everyone from Science in Our Community for organizing this and being here. They're going to help moderate. And then also thanks to Dr. Naughton, who's hiding off to the side here, who's here in the dome with me, so she can kind of read text messages and, or chat messages and that kind of stuff while I have to be running around doing other stuff, and she can read me things. Mostly I'm here to take everyone's questions about anything you want to ask. This is a live picture of the moon we have up right now, which fortunately is not in the clouds. It's still a bit bright out, but as it gets darker and some stars start coming out, we should be able to get the Orion Nebula tonight, maybe some other targets. Yeah, I have my nice Science Day shirt here. Okay, so I'm going to take the light out of my face for the moment. Here we go. I don't know. Do you want me to? I can probably stop my video, but if I need to use hand gestures or something, I'll put it back on, so you can enjoy my nice picture of me with the Easter Island heads there. That's real. I was really there. It was awesome. It was for a conference. So let's see. So yeah, here we've got the moon. This is with an eyepiece where we're seeing almost all of the moon. Let's see, I can probably move it around a little bit. There we go. Yeah, pretty much all of it. And we're used to seeing the moon with our eye, right? But when you use a telescope, you get a lot better picture, so we can really see there's really craters and everything on the moon. Especially, this is my favorite time to see the moon, when it's about half full, like a first quarter like it is now. Because you can really see the shadows, especially along that dividing line between day and night. You can really see how deep those craters are. You can even see mountains in some of them. We'll see that better in a minute when I switch eyepieces and zoom in a little more. This is with the big telescope here on campus. So this is in the dome on top of Naragi Hall. So this is actually a really nice, like 20-inch telescope. I think this is the first time I've used it in like 2.5 years because, during COVID, it's been mostly shut up. And, obviously we're still not having people on campus. Hopefully that will change. Ideally in fall, we'll do an astronomy night where people can actually come in person and look through telescopes themselves. But, we've got the next best thing with our iPhones and everything here. And you might, I think if you go to view or options or something, you might even be able to zoom in and, if you want to get it a little more full screen rather than kind of my iPhone screen size. I still haven't figured out how to get this to display horizontally on when I'm using iPhone. So, yeah, that's what we have. And hit me with questions anytime. Let's see. If you go outside right now or look out a window or something, the moon you'll see is going to be reversed from what's shown here. If I look at the sky, the left-hand side of the moon's dark and the right-hand side's lit up. If I look at this screen here, it's the other way around. It's the left-hand side that's bright. And that's because our telescope here uses a mirror, and when it goes off that mirror, it gets reflected just like when you look in the mirror. So we end up seeing everything backwards. And that can get confusing when you're trying to, look for things in the sky and then look for it through the eyepiece with the telescope or whatever. It'll get a little confused. Let's see. And when you look at the moon, especially like this, even when you look with your eye, you can tell there's kind of some dark areas and light areas and stuff. What makes the craters? Yeah, question in chat here. So what makes those craters is going to be impact. So it's getting hit by asteroids or meteors. and they come in and they're going really fast. They've got lots of energy and get this big explosion that will make this crater and then kind of throw a bunch of stuff up that then falls back down. And most of these craters are really old. So the solar system's about 4.5 billion years old. And a lot of these craters, especially on the rougher parts of the moon, are that old. Someone asked here, what's the darker shading? Yeah, so, right, like we see this light and dark, and especially at the top here, we can kind of see like the head of the rabbit, although he's upside down here. You can kind of see like there's sort of the body and the head and the bunny ears on the left. So those darker areas are actually the remains of really big impacts. So you probably had some really big asteroids hit the moon early on. And then they were so big, they really like broke through the crust of the moon. And just like Earth, you'd have magma, liquid rock underneath. And so then that magma could seep up through the cracks that big impact caused and would fill that crater. So you'd have like kind of a lava ocean, and then it would cool off. And that's really what you're seeing. So they're darker because that's really like kind of dark volcanic rock. If you've ever been to like Hawaii or, maybe, I don't know, other places where they have like lava flows, it's that really dark basalt rock because it's got a lot of like iron in it. It ends up pretty dark colored. So those are what those dark areas that like you can see, especially at the top of our image are. And then the lighter areas are also rock. I actually forget what composition it is, but not quite, not basalt, just something a little bit lighter colored. They're still actually pretty dark gray. I think those dark areas are almost black. The white areas you're seeing are really like a dark gray. It's just that compared to space, which is totally black, they look light colored. Oh, how big are the craters? Boy. So the moon is about, sorry, my don't start close. So let's see. So the moon's about a fourth the size of the Earth across. So it's about as big across as like North America, maybe about 3,000 kilometers or so, maybe a little bit more. So let's see. So that means the biggest, like those dark areas up at the top, the biggest of those is maybe a sixth of that. So it's maybe 500 kilometers across, like 300 miles across, around that. So then those craters you're seeing on the dividing line, like say that towards kind of the bottom of the image, there's a nice big one right on the terminator right on that dividing line. So that's maybe 100 kilometers across, 50, 100, something like that. So 30, 50, 100 miles. These are big craters. And you get craters of all different size on the moon. So you have ones, hundreds of miles across all the way down to actually like a couple of millimeters across, where you've had just like tiny little grains of sand come in and hit the moon. And that's because the moon doesn't have an atmosphere, so there's nothing to stop all those things. On Earth, those tiny little things burn up in the atmosphere, so you don't really get those tiny craters. You got to be something pretty big, a big chunk of rock like size of a house or so to actually make it through the atmosphere.
Does the max zoom the telescope can do?
No, we can do better than this. And in just a minute, I'll switch eyepieces, so the image will go away for a while, and I'll switch cameras. But this is a nice big telescope, so we can actually get quite a bit better. How come you don't see as many craters on the Earth as you do on the moon? So there's a few reasons. So one is just there weren't as many made because we have an atmosphere and that protects us a little bit. But the main reason is that there's a lot of different processes on Earth that kind of resurface the Earth, that sort of paves everything smooth and we start over, and that erases those craters. So well, we have water on Earth, so you have, of course, the oceans are going to raise stuff. But even on land, you have rain, you have flooding, you have lakes, you have sediments. If you had a crater, you're probably going to have a river running into it, and it's going to bring in a bunch of debris and fill it up. We also have plate tectonics. So, the continents are moving around. That means the oceans get bigger and smaller, and so they'll wipe stuff out. We have volcanoes. Again, because of that plate tectonics, we'll have a bunch of volcanoes. Volcano goes off, it covers a bunch of stuff with lava or ash. That'll wipe out the craters. On Earth, we maybe only have a couple of hundred impact craters that we know about that we can see, and they're all pretty big, all several miles across at least. Well, actually, they found some little tiny ones more recently, but mostly pretty big things. And they're mostly in places like deserts where you haven't had very much water, you haven't had a volcano recently, you haven't had erosion. So you can still see them in those places. But most of the surface of the Earth, it gets repaved maybe every 50,000 years or so on average. Some places are around longer, some not as long. The moon, the bright areas with lots of craters, they're maybe more, 4 billion years or more old. The dark areas where it did get repaved, you did have kind of lava fill up these really big craters. They're still maybe 3 or 3.5 billion years old. When we zoom in, you'll actually be able to see some craters in those dark areas.
Is the moon drifting away from Earth?
Is the moon drifting away from Earth? It is really, really slowly. Because it's moving in the telescope. Yeah, so it is drifting a little bit in my telescope here, because my telescope, actually, everything's moving in the sky because the Earth's rotating, right? So things are rising in the east and setting in the west. So this telescope will actually track that and account for it to keep things pretty much centered. But then the moon's also moving relative to the stars, so it drifts around a bit. But then the moon is actually, over time, really slowly moving away from the Earth because of tides. So the moon goes around the Earth, but then the Earth is rotating faster than the moon goes around. So the gravity from the moon is always pulling on the Earth, and it's like pulling on the ocean, and it gives us tides, so we get high and low tides twice a day because of the moon. But that's also always like pulling on the Earth against the way that it's rotating. So over time, the Earth rotates slightly slower over time. And to make up for that, that energy has to go somewhere. So as the Earth rotates more slowly, the moon gets a little bit further away to make up for it. I think if you went back like to when the dinosaurs were around, maybe 100 million years ago, a day only would have been 23 hours long, and the moon would have been a little bit closer. I forget, maybe 5 or 10% closer. So it looked a little bit bigger on the sky. The tides would have been a little bit higher each day. So on those really long time scales, it'll slow down. And I think we can even measure how fast it's moving away. But it's like, a millimeter a year or a millimeter a century or something, really slowly. So I'm going to go and try to change eyepieces and zoom in a little bit. So you might not be able to hear me because, as you can tell, this dome is really echoey. So when I'm 10 feet from the computer, you might not be able to hear anything. So apologies, I'll be back.
It's getting a closer view soon.
Yeah, so it should come into focus here eventually. There we go. All right. So now we're seeing just a little part of the moon. But let me see if I can find some nice craters for us. Yeah, so there's that day-night line. And here we can see towards the bottom of the circle there, kind of that bigger crater right off the dividing line. So that one's maybe 50 miles across or so. And we can even see, let me come back down so you can actually hear me. Whoops, now let me make sure this close up. It's starting to get dark. Yeah, so you can see kind of towards the bottom, middle of the image, there's that big crater right on the dividing line between light and dark. And if you look close in the middle of it, you can see a little mountain that's there. So what happened there is we made this crater, you hit this thing with an asteroid, pushed everything apart. It kind of acts like water in a pond where, you drop a rock in and it sends ripples out, but then they come back together and they make like a mountain, like a little a point going up, and you get that like little drop of water come up right in the middle. That's exactly what happened here, except it's rock, so it kind of froze at that point where it was making that mountain. So you've got a mountain there that's about 5,000 feet high, I think, for that one, if it's the right crater I'm thinking of. So, nice big mountain in the middle of this kind of big bowl-shaped crater. And then you can see also the edge of the crater is raised up, because on the right side of that image, the lip of the crater is still in the sun, even though that part of the moon is dark. So that dividing line from night to dark isn't quite a straight line, because some parts are higher and some are lower. So the edge of that crater are these nice high mountains, or nice high rim of the crater is still in the sun.
Someone said, what types of rocks are at crater of the moon? I don't know if that means that moon or crater of the moon national.
If you mean like Crater of the Moon National Monument in Idaho, yeah, actually, I went there this past summer for the first time. So yeah, those are like nice lava flows. I think those are basalt. So those are that dark volcanic rock. It's really heavy, really iron rich. So that's stuff that's coming up from the mantle deep inside the earth. And actually, if you look at the sea, at the oceans, the seafloor, like under the sand and that kind of stuff, they're actually made of basalt as well. This sort of heavier material. The continents on Earth are made of lighter stuff like granite and sandstone and chalk and all those kinds of things, but mostly granite. And so they kind of float above the magma. They're the pond scum that's kind of floating around.
Do we know the age of the moon? If so, how?
Yes. Yeah. So there's kind of one of these flat areas, these like lava seas, where you could see there's kind of a lot of craters outside of it. And then inside, maybe there's just a couple of craters because it's younger. So do we know how old the moon is? We do. The solar system, kind of everything, the sun, the earth, the moon, are all about 4.5 billion years old. Maybe, the earth and moon slightly less than that, but they didn't take too long to form after the sun. We know that actually because, like for the moon, we know it for sure because we've sent people there, they picked up moon rocks and brought them back. And you can look at those rocks and actually date how old they are using radioactivity. Because like for really old rocks, when they formed, you would have had, I think you do it with uranium. So they would have had some amount of uranium that you don't necessarily know. But then the uranium decays and it leaves lead behind. And you can look at how much uranium versus lead there is, and how long it takes the uranium to decay. And so you can figure out how old that rock is. And every time that rock got melted, the lead would kind of have boiled off and just the uranium would be left behind. I think you can also do it with, I forget it, something else in argon, and the argon escapes, depending how old the rock is. We know how old the solar system is from dating like meteorites that have come to Earth. We can pick them up and look at the different ratio. And we know that they've been around since the solar system formed, or at least the oldest ones have. And they're about 4.5 billion years old. The moon, we can also do it with moon rocks, and the oldest moon rocks are maybe almost that old. The youngest ones were maybe only 3.7 or 3.9 billion years old, so almost 1 billion years younger. And those were coming from those flat places, from the dark areas where it's mostly this kind of younger lava. That's maybe a little bit less than 4 billion years old. the rougher areas, the missions that landed there, then they're more like, almost 4.5 billion. We can do the same for rocks on Earth. The problem is rocks on Earth don't stick around that long because the Earth's always being resurfaced. And so, most like the sea floor, basalt from volcanoes, a lot of it's only maybe a few million years old. Even the continents, like, the Sierra Nevada, if you went and dated how old is the granite, maybe it's a few 100 million years old. But then some places you'll get really old rocks preserved. So maybe the oldest rocks on Earth are around 4 billion years old or a little bit older, but there's only a few spots like I forget where. I think there's like in Greenland and there's somewhere in Australia that have these really old rocks. And maybe in like really deep canyons where you cut down through a lot of layers. So like the Grand Canyon or what's the one in Colorado? The Black Canyon of the Gunnison, you'll get like 3 billion year old rocks at the bottom.
Can we see where Mr. Armstrong landed in 1969? Is there any traces, the flag over there?
Excellent question. So with a telescope from Earth, we can't see it because that would be too small. And there's two problems. One, we need a really big telescope to be able to zoom in that much. But second is actually seeing through the atmosphere is pretty difficult. Tonight's actually a pretty nice still night, so you're not noticing it too much. But the air is turbulent. That turbulence means the atmosphere acts like a lens, and things are always kind of jittering around and going a little bit in and out of focus. And so if you look at stars, that's why stars twinkle. It's not because the stars are changing in brightness, it's because the atmosphere is in the way and they're making it look like they twinkle. So that means there's a limit to how small a thing you can see through the atmosphere. And at the distance of the moon, I forget how big that is, but it'd be bigger than the size of anything that the Apollo missions left. So that's why, like, we put the Hubble Space Telescope in space, is because then we don't have to look through the atmosphere and you can get better resolution. If you put a satellite in orbit around the moon, though, then you can see those landing sites. And we've done that. We've sent things to orbit the moon since then. And there is still stuff there. The Apollo 11 site's actually pretty damaged because when they took off from the moon, that sent the rocket exhaust out and that kind of, scattered everything. So I don't know if the flag's still there. It might have blown it over. But there's still like footprints there from them. There's still some, the legs of the lander are still there because they didn't take those back into orbit with them. They wouldn't need those. I'm not actually sure for Apollo 11, but for some of the other Apollo missions, they left reflectors behind. So there are things they're like a series of mirrors at right angles, so they'll reflect light back to wherever it came from. And that's actually how they know how far away the moon is, because you can bounce a laser beam off of them and get some light back. And you can time how long it takes, and so you get really precise measurements how far away the moon is. And those are reflective enough you can actually do that. I think they even did that on like an episode of The Big Bang Theory. They had like their laser on the rooftop of their building and could see how far the moon was. That's really coming from those reflectors at a couple of different sites. And you can even, if your laser is good enough, zero in on just one particular site. Yeah, so there's still definitely stuff there. We just can't quite see it from Earth.
How deep do some of the craters go? Does anyone know?
Good question. Let's see. How deep are the craters? So I think for a typical crater, the depth is about 1/10 as wide as it is, so like 10% of the width, or it's about 10 times as wide as it is deep. I think that's the right number. So if you're seeing a crater that's 50 miles wide, it'll be about 5 miles deep. So, that'd be like 25,000 feet. So you get some really deep craters. At some point when the craters get too big, then they don't actually get quite that deep because stuff kind of falls back into them. And so you get like that central mountain at the middle, or for really big ones, you can even get like multiple ripples. So then they're not quite as deep. And these really big ones, like the one we're seeing in the middle there, that big dark area, that was a really big crater. And I don't know, that's, 1,000 kilometers across, like 600 miles wide. But it never really was 60 miles deep. And then it filled up with lava. So maybe, it's only 5 or 10 miles deep, or the edge is only maybe 5 or 10 miles above the lowest point, because it's kind of filled back in with a bunch of stuff. But yeah, for small craters at least, it's about 10 to 1, I think.
How big is the moon?
How big's the moon? Off the top of my head, I'd have to check, Wikipedia or something to get the exact number. I think it's roughly a quarter as wide as the Earth. And it's about 1, and then, the surface area then would be about a 16th as much as the Earth, and yeah, about that. Well, okay, maybe, yeah, that's about right, about a quarter. And I think the mass is about an 80th of the Earth, so it's only a little more than 1% the mass of the Earth, but it's about a quarter as wide. So that's roughly, what would that be? Kind of as wide as North America almost, or Australia maybe. So it's pretty good size, but not that big compared. But actually, that's really rare among planets. So our moon, of any of the 8 planets in the solar system, it's by far the biggest compared to how big the planet is. Like Jupiter and Saturn, they both have moons that are bigger than our moon, but they're way bigger planets. They're like a couple 100 times the mass of the Earth, and like 10 times the size. So it's really rare, actually, or we think it's really rare to have a moon that's that big. And like Mercury and Venus, they don't have any moons. Mars has 2 moons, but they're just tiny little things. They're just like little asteroid-sized stuff. Our moon's this really weird big.
Will we be looking at any other planets during this Zoom?
So unfortunately, no other planets for this Zoom, because they're all on the wrong side of the sun right now. So they're up at like 5 in the morning. In a little while, though, I'll go to the Orion Nebula, which is kind of like a cloud in space that's forming a bunch of and it's getting dark enough that it should be out. Let's see. Let me kind of roam around the moon. Let's see. Yeah, you can kind of see I'm looking at the bottom edge of the moon there. That sort of towards the top of the image, the craters are more round, and then as you go further down, they kind of get more and more oval shaped. And that's because the moon really is a sphere. And so the ones towards the bottom, we're seeing like more and more edge on. So we're just kind of seeing them like a low angle, and they look like an oval, but really they're still all more or less circular. So that's always kind of neat that, if you have a telescope, you can tell the moon really is round, or it really is a sphere, not just a pancake, shaped like a basketball.
How long does it take to get to the moon?
Let's see, how long does it take to get to the moon? It depends how fast you're going. For the Apollo astronauts, I think it took about 2 or 3 days to get to the moon, and then another 2 or 3 days to get back. And then, actually, Apollo 11, they only spent less than a day on the moon. The later missions, maybe a couple of days. And I think there's new missions that are supposed to be coming up like soon, like the next couple of years. People are supposed to be going back first to orbit the moon and then to land on it again. But it'll take about the same amount of time, a couple of days, maybe 2-3 days to get there. So not too bad. Getting somewhere like Mars takes a lot longer. To get to Mars, at least the cheapest way to get to Mars, with kind of the least amount of fuel that you need, takes about 9 months to get there. You can get there faster if you spend more fuel, but then that costs a lot more if you've got to get the fuel in space to burn and everything.
Has anyone asked about the composition of the moon yet?
No, I don't think so. So composition. Oh boy, really quizzing my geology skills. Trying to remember what I can about it. So overall, the composition's a lot like Earth. The rocks are pretty close to what you would see on Earth, minus a little bit. It doesn't have really any like what we call volatile elements. So like the oxygen and the nitrogen that would have been in the atmosphere is all escaped because there's not enough gravity to hold on to it. Even same with things that have kind of a low melting point, like lead and maybe gold and mercury and some other things. They probably would have been, when the moon formed, they were probably vaporized and escaped. But we do have them on there. The rocks, I can't remember what the lighter colored rocks are made of, but they're actually pretty heavy, dark things, and kind of volcanic-ish. The darker areas are like heavy volcanic rock, like basalt. And the moon has a thicker crust than the Earth because it's small, and so it cools off faster, so it's cooled more. So it's got a thick crust, and we don't see any like active volcanoes or anything. Then it probably has a mantle just like the Earth does that's kind of semi-liquid rock. And it does have a core that's metallic, but it's a lot smaller than the Earth. And even compared to the size of the moon, it's a lot smaller. So, and we think that's to do with how the moon formed. We think what happened was the Earth had formed, and then kind of another planet that was maybe almost the size of Mars came in and hit the Earth. And mostly they kind of merged into one bigger planet. That's what the Earth is now. But some of the stuff got kicked off into orbit, and then it would have come together to make the moon. And that all would have happened in like a day, that all this debris would have come together to make the moon. But that means that stuff was really hot, and so you got rid of kind of a lot of the light elements or anything with a low melting point. And the metal, the cores of those two planets that hit each other would have been a lot harder to get into orbit. So mostly the stuff like iron that our Earth's core is made of ended up in the core of Earth, and not very much ended up in the moon. So that's why the structure is a bit different.
How many craters are on the moon?
Oh God, how many craters? I don't know if you can even count how many there are. Because there's just so many. You get, all the way from hundreds of miles in size down to, millimeters, like, fraction of an inch in size. So if you try to count all the craters, billions and billions and billions. If you try to count, every crater bigger than a mile across, you could probably come up with an answer. But even that, I think, is going to be in the thousands. And I don't have a good estimate off the top of my head. What does Wikipedia tell us? Okay, so it says 9,000 craters, but those are probably things bigger than a mile or a kilometer or 10 kilometers or something. There's got to be some size cut off. So we'll have more questions on the moon. I'm happy to take those. But maybe if everyone's gotten their look at that, I'm going to try to find the Orion Nebula and get our telescope focused on something different and see what it looks like. I've never actually done it with the iPhone or a camera with this telescope. So we will see how that goes.
They're asking, is that the nebula?
So this is the Orion Nebula. And it's a little tough to see even on this. It's probably because it's so dusty. But yeah, you can kind of see it. So there's sort of a group of like 4 stars there in the middle that you can see. There's like a line of 3 on the bottom, and then there's that little cluster of 4 together. And then you can see that blue area around it, that kind of extended thing. And that's real. That's not just like, the optics or something. That's real, like gas that's out there in space. And this is actually pretty far away. So this is about 1,000 light years away. And so those 4 stars in the middle you're seeing, they're actually super bright stars. They're really much, much brighter than the sun, like 10,000 times as bright as the sun. And in fact, I think there's really like 10 or 12 stars there. Each of those 4 you can see are really a double or a triple system. They're big, bright, what we call O stars. They're really pretty blue in color, although they don't look like it here because there's a lot of dust in the way. They're just pumping out light, and they aren't going to live very long. So stars like that, they only live for maybe 3-5 million years. And then they're going to go supernova and blow up. And when they blow up, they're going to push all that gas that's around them away, and this cloud is going to get disrupted. But we're only seeing those very brightest stars. There's really lots and lots of stars that are there, and they're still being born. This is a star-forming region, and I think the total cloud is like a few thousand times the mass of the sun. So it's going to make a few hundred or 1,000 stars in total in a few million years, and then it'll get disrupted and blow away. That's even starting to happen already. So those stars are so big they have, like the sun has solar wind. These stars have wind also, but it's much to push out all the gas. And you can even see, so you see that kind of blue region in the middle, and then on the right-hand side, you can see it's really dark compared to the other side. That dark part is actually where it's really dusty, and there's like a really dense dust cloud in space there. So we can't see anything there in the optical, even though there's a bunch of stars in there. They're just not showing up. If you look with an infrared telescope, like the Hubble's telescope in space or something that's longer wavelengths, you can actually see through that dust and see all these little individual stars. So other than those really brightest stars, we're seeing gas in the dust. But actually it doesn't look too bad, zoomed in here and everything. Yeah, better than I was expecting with this camera, and jerry-rigged setup I have and everything. So yeah, pretty good. I'm impressed by your phone, Dr. Naughton.
There's moon questions still.
Sure. Yeah, we got a few more moon questions. We can do a couple more of those.
If you have any about the nebula, please drop them in the chat. So how does a moon form for each planet?
Oh, good question. Because there's actually a few different ways. So the Earth's moon, we think, formed from an impact. You had two, early on in the solar system, long time ago, you had two planets that were kind of newly formed, but their orbits were probably pretty close to each other. Especially early on, it was like billiard balls. You had things bouncing around. Something about the size of Earth got hit by something about the size of Mars. It throws a bunch of debris up. The Earth would have had a ring for a little while, like Saturn does, but most of that stuff then under gravity would have come together and formed the moon. So that's one way. You can do it by impact. Another way you could do it is you could just capture something into orbit. That might be how Mars got its moons. It has these two little things that are they kind of look like asteroids, so they might actually be asteroids that got captured, or maybe they were one asteroid that got captured and then it split apart from the gravity of Mars. Neptune has a really big moon that's called Triton. So Triton is definitely captured. It was actually a planet or a dwarf planet on its own, because it looks a lot like Pluto. It's like Pluto, but about 1.5 times the size. And so we're pretty sure it was its own thing that had formed and was orbiting around the solar system. And then it got close to Neptune and it got sucked in and captured into its orbit somehow, probably scattered off a bunch of other moons and ended up orbiting Neptune. So that's the second way. And then the third way, which for the giant planets is probably how most of their moons formed, is it could form around the planet out of a disk, just like the planets form in our solar system around the sun. So you have a bunch of gas and dust and rocks orbiting around, and then gravity will kind of start pulling them together and you'll get bigger lumps, and then those lumps collide and they build up to protoplanets, and then those make planets. For a planet like Jupiter, you could have the same thing. As Jupiter's forming and it's growing bigger, it'll have a disk of material orbiting it, and then some of that stuff will be left behind and it can form into big moons. So they really form along with the planet. And even though they're big moons, compared to the mass of the planet, they're almost nothing. I mean, they're like all of Jupiter's moons together are 1% or 0.1% of the mass of Jupiter. Actually, that's not too different from the solar system. All the mass of the planets put together is about 1/10 of the mass of the sun, 0.1% of the mass of the sun, 1/1000 of the sun. So, you got a big enough planet, you can make things that way. For the little rocky planets, we don't think that happened, like Earth, but Jupiter, Saturn, Uranus, Neptune, probably made moons like that. And then Neptune ended up capturing a big moon that probably got rid of a bunch of its other smaller moons.
Do nebulas fade out?
Oh, do nebula fade out? Yeah. So eventually it'll be gone. So we're seeing it as a nebula, well, for two reasons. One, there's a bunch of gas there, and then actually two, because there's those big bright stars in the middle. They're actually really hot. They're pumping out a bunch of UV light, and that UV light makes the gas in the nebula like fluorescent, like a fluorescent light bulb works. So I think the green bluish color we're seeing there is actually oxygen getting lit up. And a little bit further out, it'll look kind of pinkish. Like if you do a long exposure, especially, looks kind of pinkish. And that's actually hydrogen being lit up. So eventually, once the gas, one, if those stars went away, then the nebula would fade away. Or if the gas gets blown out, which will happen once those stars go supernova, then the nebula will fade away. So this kind of nebula, where it's forming stars, only lasts for a few million years, because basically once the first stars start going supernova, it blows everything apart. There can be other nebula that are coming from like an individual star that's dying. And those only last for a few thousand years, maybe 1,000, 10,000. Because then the star that's making the gas light up will fade away and disappear. And the gas will kind of disperse eventually. So yeah, nebula, they last a long time on human scales, but a short time on compared to the life of the galaxy or the life of stars.
You already meant, but how far away from Earth is the nebula? You said 1,000 light years?
I think it's about 1,000 light years. And this one's neat. So you can actually see this with your naked eye if you're somewhere pretty dark. So this is the Orion Nebula because it's in the constellation Orion. So if you look at Orion, you can see like Orion's belt is 3 stars in a line. Those are not the 3 stars you're seeing here. But you can find that in the sky pretty easily. And then if it's dark enough, if you look below Orion's belt and it's a little bit kind of on the left-hand side, there's another line of 3 fairly faint stars. And the Orion Nebula, what you're seeing here, that group of 4 stars, and on all of this, is actually the middle star out of those 3. So it's kind of like you have Orion's belt, and then Orion's dagger or sword hanging down, this other line of 3, and this is the middle star of the dagger. So these stars together are bright enough you can actually see them by eye. And I think they're actually some of the most distant stars you can actually see with your other than when they're all together in a galaxy or something. Even the brightest stars you could see individually would be like some big red giant or red supergiant or something. Only maybe 1,000, 2,000, maybe 3,000 light years away, maybe not even that. So this is actually quite far for your eyeballs.
How long does it take to make a star?
How long to make a star? It's not that long. Mostly it takes a long time for the conditions to be right. You need to have a big cloud of gas like this. So maybe you have 1,000 solar masses of gas. And you need to wait a long time for it to cool down and condense and not have it get just shredded as it's orbiting around. But once you have that, it kind of goes faster and faster the colder it gets. So it gets colder and it can radiate away more, and that keeps happening. And it'll maybe get all the way down to less than 100 degrees above absolute zero. So, we're at, probably a little warmer. We're at about 300 degrees above absolute zero, 300 degrees Kelvin. This cloud will get all the way down to maybe 100 or maybe 30 degrees or maybe 10 degrees. And then it's getting really, really dense and stars will start to form. So to actually, then what happens is the cloud starts breaking up into individual little clouds. And each of those will end up making 1 or 2 or maybe 3 or 4 stars. And that maybe only takes maybe a couple 100,000 years once you get to that point for the gas cloud to contract down into a star and then actually start fusion, and then it kind of becomes a star. But then it'll still be really dusty and it'll kind of be in like a dust envelope, and that'll last for maybe a few 100,000 more years. And that's when it's like making planets and making gas giants and Earth-like planets and everything. And then the star will really get going, and the solar wind will kind of blow that stuff out. Maybe you've got 100,000 years or so to like make the star and make all the planets and everything. And then maybe the rocky planets, they can kind of take a little bit longer. They can maybe take 1,000,000 years or so to form. But like the gas giants, you've got maybe 100,000 years. And same for the star. It doesn't take too long once it really gets to, okay, this clump is dense enough to make a star. It's fast on the scale of the universe.
Is Earth affected in any way by the nebula?
Not really by this one. This is far enough away. Let's see. Eventually, those big stars are going to go supernova. When that happens, it'll be cool because we'll see it. It'll light up the sky. But I think they're far enough away. It's not really going to fry the Earth already. If we were a lot closer, like say we were only 10 light years away from something like this, then we definitely, we'd get fried when one of them went supernova. We'd get maybe not, like the oceans would boil or something, but enough that it would have like an impact on the atmosphere, maybe cause an ice age, maybe blast off the ozone layer, bad things. But for a supernova, we'd have to be really pretty close to it. So it's very unlikely that would happen. But the Earth probably formed in a nebula just like this one. That's, most stars form in these kind of conditions. Exactly what was going on in that nebula definitely affected the Earth. So it'd be like, why does the Earth have kind of the amounts of different elements we see? Well, that would be because that was what was in that nebula, and that formed the solar system, and then that formed the Earth. Why is the sun just one star instead of 2 or 3 stars that we're orbiting around? Well, that's probably because of the conditions in the nebula right where the sun formed. Why didn't, some other star come along and strip off all the planets and send us out into space where we'd just be some cold little dead rock? Well, that has to do with the conditions in the nebula. You kind of needed to form in the right place at the right time for like life and planets and everything to be possible. Although planets seem pretty common around stars, so maybe not that special.
What color is the moon?
Oh, what color is the moon? So the moon is actually pretty dark gray mostly. It looks white in the sky because we're comparing it to space, which is really definitely dark. So it's a lot brighter than that because it's reflecting sunlight. But really, if you look at like the photographs of the astronauts on the moon, when they get moon dust on them, it's really a pretty like darkish gray color. Maybe like fireplace ash or something like that. Maybe not quite that dark, but kind of a light colored, like campfire ash. And then the dark places on the moon. So when you look at it, you can see those big dark areas that we were looking at before. They're really quite dark. They're almost like charcoal colored. Not quite black, but pretty close. Because they're this like volcanic lava flows, and just like we have lava flows in Hawaii, they're this dark, almost black color.
How long is a day on the moon, and why?
Yeah, excellent. So a day on the moon lasts a month. So the moon takes a month to make an orbit around the Earth. But the same side of the moon is always facing towards the Earth. So when we look at the moon, it's always the same thing pointed at us. Part of it might be lit up, part of it might be nighttime, but we're only seeing that same one side. And that's because of tidal forces. Like there's tides on Earth because of the moon. There's also tides on the moon because of the Earth. But the Earth's a lot bigger, so those tides were a lot stronger. So they actually made the moon stop rotating relative to the Earth. They kind of froze it in place. So only one side is pointed at us. And so if you imagine, a person walking in a circle around you, if they're always going to keep facing you, they have to rotate one time every time they go around. That's exactly what the moon does. So the sun only rises and sets once every month on any given spot on the moon. So like right now, on that dividing line between day and night, where we're seeing the crater on the moon or a bunch of craters, that's where the sun is just rising right now. And it'll be daytime there for 2 weeks, and then the sun will set, and then it'll be nighttime there for 2 weeks, and then it'll rise again.
What causes the phases of the moon?
So the phases of the moon are due to its position relative to like the Earth and Sun, and just how much of the day side of the moon we're seeing. So always half the moon is lit up and half the moon is dark. If you go out tonight and look at it, we see half of the day side and half of the night side. So it looks like it's half lit up. That's because we're kind of looking at it edge on. So it's like basically there's like a 90-degree angle between the sun and the Earth and the moon and the Earth. When it's a full moon, then we're seeing the whole daytime side of the moon. It's all lit up. And that's because the moon is on the opposite side of the Earth as the sun. So we're seeing it all lit up. Then if it's a new moon, it's like the beginning of the month, then the moon is in the same direction as the sun. And so we don't see it at all because, well, one, it's near the sun, so we really can't look there and not hurt our eyes. But also because we're seeing the night side. So the lit up side of the moon is always facing the sun, but we're on the other side of the moon, so we just see the night side. So you start out, then a little bit later it'll be a crescent, and the lit up part of the moon that we see is always facing the sun. So like if I went out tonight and I look at the moon right now, the right-hand side's lit up, and that's pointing towards the west, and that's because the west is where the sun just set, so it's pointed towards the sun. When it's a crescent, the lit up part of the crescent, the bottom of the crescent is always towards the sun. Then, it gets later, it gets more than half, and then it gets to a full moon, the lit up side's facing the sun, but the sun's behind us, so we see all the lit up part. And then it'll go on the other side, it'll be trailing the sun. And you'd see like a crescent early in the morning, and it'd be the left-hand side would be lit up, and it'd be pointing towards the east because that's where the sun's going to rise. So it's still pointing towards where the sun is.
What telescope are you using now?
Oh, so this is the telescope on campus. It's a nice big one. So this is a 20-inch telescope. So it's a mirror. Well, it's a couple of mirrors, but the main mirror is 20 inches across. So almost. So it's a nice size one. So you can gather a lot of light with that. Doesn't really actually make the resolution any better because that's mostly set by the atmosphere. So like in the past, on some of these nights, I've used like an 8-inch telescope or something. And really the resolution was the same, but it's going to look brighter at the same magnification when you use this one. So you can see fainter things with a bigger telescope. So Orion looks really nice in this one. I don't really have to mess with the camera too much to get it to show up.
What is the difference between a moon and a planet?
Oh, good question. So I think the only really real difference is, there's some things that, what makes a planet or an asteroid or something. But really, even asteroids we call like minor planets, and then there's dwarf planets, and then like, major planets like the Earth. So a planet is something that orbits a star, or in our solar system, something that's orbiting the sun. And then a moon is something that's orbiting a planet. So if the Earth wasn't here and our moon was just going around the sun on its own, we'd probably call it a planet. It looks like a planet. Maybe we call it a dwarf planet or something. But it's because basically the moon feels more gravity from the Earth than from the sun. So it goes around the Earth faster than it goes around the sun. And so that makes it a moon. And we have planets that have moons. We have dwarf planets like Pluto has moons. A lot of other little dwarf planets have moons. We even have asteroids that have moons going around them. We have a big asteroid with a little asteroid orbiting around it. I don't think we have any moons. I don't think there's any moons that have their own moons, at least not permanent ones. But you could. Other solar systems might have, a big planet with a moon going around it, and then a little moon going around the big moon. But none that we know of so far. Yeah. So here it's just a little more zoomed out. You can still see that. There's that blue area in the middle. That's what we were seeing before. And you can still see that group of 4 stars and 3 below. And then I'm trying to get some kind of log exposures, because there's really a lot more gas than just that blue part. There's really this big red, like extended part, but it's really faint, so it's hard to see. But in a long exposure can, it doesn't really show up on the screen. Yeah, you're kind of overexposed, but you really don't quite see. That's our nice little Orion Nebula there.
Thank you so much for watching. Please follow us on social media to find more about our upcoming events.